please give him a warm round of applause.
Yeah, thank you. And I'm very happy to be here. I was here in Sonthofen a year ago, and I think I recognize some faces. I'm happy to be back. Okay, good. So let me tell you a little bit about measurement-based quantum computation, which kind of nicely ties in with what Sophia has told you already. So yeah, let me just kind of introduce the subject a little bit. So cluster states are entangled states on a grid of qubits, like so. So this is every dot here is a qubit. And the question is, what can you do with the entanglement in those states? And there's a bunch of things. So here's an example. You can, if you have two locations you like to entangle in a bell-type fashion, you can do that. You can measure qubits nearby in this ribbon between the two in a certain pattern. You measure a bunch of qubits in X and a bunch of qubits in Z, and that creates a bell state between them. And that would work regardless where these qubits are located. Yeah, so that is something you can do with the entanglement in those states. Here is another thing. So this is the connection between cluster states and surface codes. So Sophia introduced you to the formalism of quantum error correction with stabilizer codes. So this is an important error correcting code, surface code. We will hear more about it in the second part of this presentation. Okay, so you can get into the code space of that surface code by measuring half the qubits in the checkerboard pattern here of X and Z measurements. So that's another thing that you can do with local measurements on cluster states. And so the question is, how far can you take this? Yeah, and you can take it at least as far as universal quantum computation. So that's basically what I want to talk about. So the 2D cluster state is a computationally universal material, and you can imprint any computation on it that you like by choosing the measurement bases in all the places. Okay, and maybe you want that to be fault tolerant also. And the easiest way to get fault tolerance in addition to universality is to go one dimension higher up. You could do this in three-dimensional cluster states. And I've just kind of adjusting a little bit to what Sophia already told you. I think I'm going to tell you a little bit about it. I have no idea how that will work with time, but let me try. Good. So here's the overview. So the outline of what I want to say. So I have a bit of an overview, and I want to be brief in where I overlap with Sophia, so that I mean, a little bit of review is nice, but I also want to tell you a few new things. Good. So we have the universality proof, or I will just maybe talk a tiny little bit still about it. And what I want to pick here is this randomness of measurement outcomes and adjustment according to those. So I want to tell you a little bit more about that beyond what you have already heard. Then there's a piece that is not here, and that is about fault tolerance. So I tell you about that. And then the third part, and that if it all works out with the planning, will be after this bit of break. Okay, so 3 parts altogether plus the overview. So let's get started. Okay, so this is what I'm going to tell you here, measurement-based quantum computation in a nutshell, cluster states you already know, and maybe a bit of background about early experiments. Good, so before we begin, let's just kind of take a step back and think about what's going on here. So in quantum mechanics, we have 2 evolutions in quantum mechanics. We have unitary evolution according to the Schrödinger equation, and we have projective measurements according to the Dirac projection postulate and the Born rule. These are 2 extremes, and then we have everything in between. The former is deterministic and reversible. Yeah? Every unitary, at least in principle, can be reversed Measurement is the opposite. It's probabilistic. You don't know which measurement outcome you're going to get, and it's irreversible. Yeah? So let's just look at that a little bit. You have some quantum state here of 1 qubit, so you can visualize it in the Bloch sphere. You measure, and you get either up or down, and you have no way of knowing where you came from once that measurement has taken place. Yeah, so they are very different, but computationally, they amount to the same. You can build quantum computation on this, it gives you the circuit model, or you can build quantum computation on this, and that gets you to measurement-based quantum computation. And that's what we want to talk about here. Okay, so now, broadly speaking, what's going on? So here is the 2D cluster state back with a little bit of extra information. But maybe the main points first. So yeah, you have this universal substrate. For now, it's going to be the cluster state. And then you compute by measuring the individual qubits. Yeah, so information is written onto that cluster, namely, chiefly, which quantum algorithm you want to implement. And then that quantum information is processed and read out by 1 qubit measurement. So everything you do by the 1 qubit measurements. Okay, so that's basically what it is. And then, of course, you need to prove that this gives you what you want. And Sophia told you already quite a bit about it. I may go over some of this. But let me give you an intuitive picture. So why is all this coloring here? So first, we see lots of arrows. So we have arrows pointing at us, and we have arrows pointing up and down and to the side. What does that mean? So that is the measurement basis. Yeah? So pointing up or down is a measurement in the x basis, and when the arrow is tilting, this means a measurement moving towards y. Yeah? So you have kind of arbitrary linear combinations of x and y. And when you have this arrow pointing at you, that represents a z measurement. Okay, and so the z measurement, their effect is basically to remove these qubits. So that's also something that Sophia showed you already. When you do a z measurement, this is practically as good as if this qubit had never been there. So what you're left with is this grid, or this network. And this already begins to look like a quantum circuit. You have these wires running from left to right, and indeed, logical information is teleported along as you measure, and then you can couple these wires by these bridges, and that will make entangling gates. When you change the measurement basis, you do 1 qubit rotations. So this is the picture we want to develop here, the measurement-based quantum computation as a simulator of quantum circuit. That is how you do the universality proof. Okay, good. So let me just tell you a few characteristics of the computational scheme. So first thing, and that was also already alluded to by Sophia, measurement-based quantum computation has an appetite for qubits. Yeah? So you use more qubits than you would in the circuit model. And that comes precisely from that picture here. So you can think of it, when you think of it as a circuit simulator, as a quantum register in the vertical direction and time in the horizontal direction. So yeah, so the number of qubits that you need is the number of qubits in the circuit model times time. Yeah, so you have an increased number requirement. Okay, as soon as I say that, I mean, of course, you can mitigate that, and basically something you can do. And in many ways, this is a useful thing to do. You can, while you burn your cluster measuring it, I mean, you're releasing lots of qubits, and you can bring them back and reattach them on the other side. So you have a sort of conveyor belt architecture where cluster state is measured on the left and reattached to on the right, and it's using all the same qubits. So that is useful in a number of ways. Mostly it is useful, although I'm not going to go into it today, in schemes of computation where you have probabilistic heralded gates. Yeah? So that is something like this. Yeah? So this is KLM. So if you're thinking about quantum computation with photons, then you would have to think about probabilistic heralded gates. So what this means is the gates sometimes succeed and sometimes fail, and they tell you what they do. So that is a kind of a benign form of error, but it's bad enough. Okay, and so you can mitigate its effects by making a cluster state. So you have your potentially failing entangling gates, you use them to extend the cluster state. So sometimes it fails and you shrink. Mostly it succeeds and you grow. Maybe you grow on average. This is what you do on the right-hand side. And on the left, you shrink the cluster state by measuring. And you have a safety distance between the two. Okay, so this is how you can work with probabilistic heralded gates. Okay, here's another thing that measurement-based quantum computation has been used for, and this is work by N. Broadbent and company. So suppose you have a real-world quantum modem, which is basically good enough to create one-qubit states, individual one-qubit states, unentangled, and send them through a line, a telephone line, a quantum telephone line or something. Suppose that's all you have. But there is things more powerful than you in the world. There are these omnipotent quantum servers that offer to do a computation for you. And so you want to delegate your computations, but under two conditions. You want that this device is not cheating you. You want it to do exactly the calculation you care about, and also you want it not to learn what it computes. So measurement-based quantum computation gives you that protocol. So you can set it, you can derive such a protocol for measurement-based quantum computation. So this is something that is possible. Okay, and so then we come to three-dimensional cluster state. I already mentioned they are fault tolerant, and so you can think of them in terms of fault tolerant quantum computation any way you think about it. Maybe local architectures, maybe distributed architectures. Yeah, so there's lots of wiggle room there. Okay, so that was kind of the overview, and now let's get into the more technical parts. So I will be brief because you heard it already. Yeah. So this is a way to create cluster states, prepare eigenstates of sigma x, and then switch on the Ising interaction for a certain time. And yeah, you choose the time independent of what your lattice dimension is, what your graph really looks like. The time is always the same. And once you're done with that Ising type interaction or conditional phase gates, same thing, then you have created your cluster state or graph state. Good. Okay, examples. These are the examples that you've already seen. Bell state, Greenberger-Horn-Zeilinger state. Here, maybe as a first indication that this has to do with quantum error correction. So this graph state here represents a code word in the Steen code. Good. Okay, the definition you also have already seen. I'm reviewing it here because we'll need it for fault tolerance. So we will use both. We will use the creation procedure to explain certain things, creation procedure for cluster states. We'll use the stabilizer definition of cluster states to show other things. So you'll mostly use it for quantum error correction. So let me just remind you, cluster states are stabilizer states. That is, they are defined by a bunch of such eigenvector equations. Yeah, and this is what the stabilizers look like. They have an x in the center and Pauli phase flip z's on the neighboring qubits. Good. Two experiments. So I'm mentioning just two early experiments. They were, one was made in Munich in the group of Emanuel Bloch and, so with Markus Greiner. And so that was an experiment in the early 2000s. So to my knowledge, this is the first experiment that created cluster states in cold atoms, with cold atoms and optical lattices. They didn't use it for measurement-based quantum computation. At the time, they wouldn't have had the single site resolution for that, but they created cluster states and showed that they had created them. Good. So the other experiment was performed this side of the border, and it was a measurement-based quantum computing experiment, the first, and it was done with photons. So, yeah, so indeed, measurement-based quantum computation has taken root, I mean, from a applications point of view, has taken root mostly in photonics, and that's because it gives you a way to handle probabilistic heralded gates, a very convenient way of handling them, and that's a situation you face in quantum computation with photons. Okay, so they did up to a little Grover's algorithm. Good. Okay, so let me now tell you, so this is kind of the overview. Maybe I should have a break and ask you for a question, but only to get a sip of my coffee. But are there any questions? Okay, doesn't seem to be the case. Okay, so then about universality. Yeah, so let's see what there is to do here. So we can kind of reduce this computation to its parts and explain it that way. So the first thing is we remove the qubits measured in ZE. Yeah, so we have to show that measuring them in the Z basis really gets rid of them. That is something to show. And then we are here dealing with this network, and it really already looks like a quantum circuit. So we want to identify the parts. Yeah? So we want to say, okay, this is a C0 gate, this is a rotation, this is just wire doing nothing but the identity. Yeah? So we want to chop up the remaining network into these pieces. Okay, and then we have to talk about what the effect is of the random measurement outcome. So again, let me just recap that. It's an important point. You can choose the measurement basis in quantum mechanics, but not the measurement outcome. So the measurement outcomes will be random, and so maybe that influences your processing. So you need to think what to do about that. Yeah, you can't just ignore the randomness of these measurement outcomes. Okay, so in total, you would have to do 6 things. Yeah, you have to show that you get a universal set of gates. Maybe you start with the simplest. You want to show that you can at least do the identity. And once you have shown that, then you extend it to rotations and to entangling gates. So that would be the parts. And the remaining 3 steps, they are for the composition. Yeah? So removing qubits measured in Z, then there's a step composition. And what does composition mean? You have a measurement pattern for one gate, you have the measurement pattern for the other gate, and you want to show that when you compose these measurement patterns, that implements the composition of the gates. That's also something that you need to show. And then finally, you want to deal with the randomness. Okay, so I was planning to do these 3 things, but now, given what you've already heard, I think I want to go one more time across this step 6, and I want to be, I think I leave that out entirely, and I will be very brief over here. Good. So this is what I'll touch a little bit, and that's what I really want to go back to. And once we're done with that, I will then move to 3 dimensions. So that will constitute the universality proof, or the parts anyway that we'll be looking at, and then I'll talk about fault tolerance. Good. So wire. Okay, so you've seen this already. So this is the protocol. So we have a quantum state, a cluster state with input, which you see defined here. So we have pluses, eigenstates of X, entangled with conditional phase gates, but you have an arbitrary quantum state to begin with, and that is teleported to this other qubit by these measurements over here. Yeah? So this protocol, shown as a circuit, it looks like this, and we want to show that it does indeed what it is supposed to do. And that, by a few simple tricks, rearrangement of operations can be traced back to teleportation. So you see how these various things are related, and you saw it already. Good. So let's talk about the one qubit rotations. How did that work? So so let's look at this thing. So this is a familiar object by now. So we have a cluster state with input created from a bunch of pluses and an unknown quantum state through entanglement that is created by conditional phase gates. Okay, and so now what we do to understand that, it happens in an 8-qubit Hilbert space, so it is a fairly simple situation, but still, let's break it up into smaller pieces. So what you can do is, going from here to here, you you change the temporal order of commuting operations. Yeah, that doesn't make a difference. And so what we do, going from here to here, is we exchange the order of the conditional phase gate and that measurement. You see this here versus here. And also, we exchange the order of that preparation and that entangling gate up here. Yeah, so that's what you see here. Okay? And so now, after we've done this rearrangement, this equivalent rearrangement of operations in time, we see that we have kind of the same structure twice over. Yeah? So this circuit here appears twice. And these steps are called half teleportation. So we have reduced what we have to explain to a simpler thing. And that simpler thing we will discuss now. Okay, so now let's look at one of these blocks, and let us further specify the observables. So up to that point, the observables were unspecified, and now we specify them. We do not allow arbitrary qubit measurements. We only apply measurements of a certain kind, and that is what they are. So they are x's conjugated by rotations about the z-axis. Yeah? So in other words, these are linear combinations of x and y. Okay, and so the measurement of such an observable we can represent as a unitary gate, a rotation, preceding a Pauli measurement x. That's the first equivalence we see. And then furthermore, we have the commutation between this rotation and the conditional phase gate. So we can propagate it back in time without changing anything. Yeah, and so it's just a rotated state with this circuit applied to it. And that's now really a very simple thing. It's a 2-qubit stabilizer circuit, so it's not too hard to figure out what it does. Okay, and so here's what it does. It gives you the rotation you had in mind, plus this byproduct that was already mentioned by Sophia and the Hadamard gate. Okay, so this is what such a little block does, and now we want to know what the combination does. Okay, and it's just the same structure repeated twice over, and now it is important that we have these Hadamards in here. So going from here to here, the first step is to insert an identity in forms of Hadamard squared, and then put brackets, and so what we see is that the latter z rotations by conjugation becomes a rotation about the x-axis. Yeah, that's the main thing that happens. And also our byproduct changes from z into x. So we have byproducts of both types. Okay, good. So that's kind of the important thing. We can do rotations about the z-axis and rotations about the x-axis. And which one we do doesn't have to do with the measurement basis. In this case, what it has to do with where we measure. Yeah, there will be sites for performing X rotations and sites for performing Z rotations. And what the measurement basis chooses is the rotation angle. Good. Okay. So overall, what we find is that we can do both X and Z rotations and that these rotations alternate. Yeah, good. Okay, so and I wanna, going from here, I wanna go towards a point that has to do with the adaptation to measurement outcomes. So there's one thing I want to end this review of the universality proof with, and then that ascent now starts here from this picture. So, so this is the remaining thing that I want to do in the universality proof. Good. Okay, so I think I said this a couple of times. In a quantum measurement, you can choose the basis, but not the outcome. So you'll get random outcomes. And we've already seen what they do. They give us these additional Pauli operators, yeah? So what we call byproduct operators. So how do we get rid of them? Okay, so this is, this is how to get rid of them. So that's what you see here. So we have our measurement-based quantum computation here on a one-dimensional cluster chain, and on top, you have the circuit that it simulates. So you have Z rotations, X rotations alternating, but then you have these extra things, these random but heralded byproduct operators. Okay, so now let's get rid of them. And let's do this. So the basic principle for getting rid of them is to propagate them past the end of the computation, after the final measurement, because what happens after the end of the computation obviously doesn't matter for the computation. So that's our strategy. But in doing so, under propagation, these byproducts leave a trace. And what we want to do now is investigate that trace. Okay, and just for simplicity, let's assume this would be the only byproduct to deal with, and miraculously, by getting the preferred measurement outcome, the other byproducts don't appear. So let's just focus on one thing, because the discussion of all the others is just the same. Good, so we have this byproduct, and we know that we have it, and we want to get rid of it. So what do? We move it forward. And so we move it forward by conjugation. So we are conjugating these gates in the middle under these byproducts. And since the Pauli operators Z and X anti-commute, so in the exponent we get a minus sign, and so the rotation angle is flipped from what it was to minus itself. Okay, so we do this one more time. So we want to get here, so that's the goal. We have just made the first step. Okay, we do this one more time. Okay, so this time the rotation and the byproduct commute, so there's no change in the angle. We do this one more time. We observe the same flip of angle as we had before, so no change, no difference. Change, yes. Okay, and so then it also commutes with the measurement, so no change there. And now it is where we want it. It's past the end of the computation, so we can just remove it. Okay, and so the summary of what happened is this effect. In its path towards the end of the computation, this byproduct operator has flipped a bunch of measurement angles. So that is really the effect, and that we now need to deal with. Yeah, okay, sorry, I just said that, okay. And so, so what we observe now, I mean, as a formula, we have, so let's focus on this qubit over here. So the rotation angle of the rotation we want to implement is the measurement angle, the angle that defines the measurement basis at qubit 3, times a factor plus or minus 1 that depends on the outcome over here. Okay, so we get a kind of a random rotation angle if we don't think about it. Okay, but in the same equation, we can move this factor of -1 to the other side, okay? And so now, the way we read this equation is, I mean, maybe I should have said this explicitly. So here, the measurement angle has defined the rotation angle together with this random measurement outcome. So let's not do that. Let's put the -1 to the other side. And so what we see here is that the rotation angle that we want and want to keep defines the measurement angle at that side. So that measurement angle is now not fixed from the beginning, but it is the rotation angle that is fixed times a random factor that comes from the prior measurement. Yeah? Good. Okay, so this is how we adjust to the randomness. We leave the measurement angles adjustable, and in this way let those byproducts propagate out without harm. Good. Okay. So yeah, so this tells us something about temporal order. So the measurement basis over here needs to be adjusted to what has been measured over here. So the outcome from that measurement must be known when that measurement is taking place. So it means this qubit must have been measured before that. Yeah? So this adaptation business tells us about temporal order in measurement-based quantum computation. Yeah? So the randomness of measurement is the cause for temporal order in the scheme of computation. Yeah, okay. Okay, I think I got a little bit ahead of my slides. Yeah, okay. So that is the universality proof. I mean, you see, I left out a couple of things, but basically this is how the whole proof would be structured. Okay, good. This is what maybe the main message of why I reviewed that part. So randomness of measurement is the cause for the temporal order in measurement-based quantum computation, or the need to adjust to that randomness. Good. Yeah, so now is temporal order in measurement-based quantum computation different than what you have in the circuit model? And the answer is yes. And from what we have, this is now easy to understand. So we can just see, okay, so this is the general situation of the 1-qubit measurements. So they are all in the XY equator of the Bloch sphere. And so, yeah, and all that ever happens is that this measurement angle is being flipped into minus itself, or not. So these are the two possible choices of measurement basis. Okay, and so now we can ask ourselves the question, are there any bases that do not change under this flip? Yeah? If there are such bases, they would drop out of the temporal order because there's nothing to adjust. And indeed, there are such bases. So there is the eigenbasis of sigma x, yeah? So just two sigma x eigenstates. Yeah? So you flip that vector, it doesn't change. And then there is the eigenbasis of sigma y. So here there is an effect on the states of the basis, but the basis itself doesn't change. Yeah? So the two eigenstates are just interchanged. So for these two bases, no adjustment of the physical operation doing the measurement is necessary. And that's why these two bases, they drop out of temporal order. So if a qubit is measured in one of these two bases, you can measure it at the beginning. So there's no need to adjust it to anything. And so we could ask, well, what gates are implemented with these two measurements only? And they are all the Clifford gates. Yeah? So here's the CNOT example, here's the Hadamard, there's a bunch of more Clifford gates. So I guess you need one more generator for generating the Clifford group. And all of this is implemented just doing X and Y measurements. So if you're simulating a quantum circuit, the Clifford part of it does not contribute to its temporal order. I mean, to the temporal order of the simulation. Good. Okay, so I think that was the point I wanted to make, and so this is the end of the first part of this presentation. So are there any questions? I mean, are there questions, sorry. I see an arm going up, yeah? Actually, yeah. I mean, if you really don't like to go to, I mean, it's a trade-off, like usually. So if you absolutely don't want to go to 3 dimensions, you don't have to. So what you keep in, maybe it's a good thing to keep in mind is if you have measurement-based quantum computation in dimension D, that simulates the circuit model in dimension D minus 1. So remember that initial graph that we had. So if you do this on a 2D cluster state, you are mapping to the circuit model on a line, yeah, with nearest neighbor gates, basically. And so there is a threshold result for such a setting. There's a result due to Gottesman time back. But it has a very low threshold. And then this whole scheme has overhead still, and so I think you're getting to a threshold value of 10 to the minus 8, which might be discouraging from another perspective. So that's what you get when you do 3D. You get a very large, I mean, a comparatively large threshold value, more like 10 to the minus 2. Yeah. And then maybe that's coming up. So when you're mapping the 3D cluster state to the circuit model, you get fault-tolerant quantum computation on the surface code. Yeah, and so it's kind of, or the surface code analysis carries over, or vice versa. Yeah, so that's why. I mean, you can go to 2 dimensions if you are prepared to incur a very low threshold value. Yes? Sorry, I started thinking about your question, but then it continued. Can you please reiterate?
Is there a link between Clifford gates being simple to simulate classically and the lacking of the requirement of temporal order in measurement?
Yes, there is. So why are Clifford circuits easy to simulate? It has to do with kind of conjugating Pauli operators under Clifford unitaries. So that's the definition of the Clifford group. Any Clifford group element maps all Paulis to the Paulis. And that update is also efficient. You can efficiently follow. And that has a counterpart in measurement-based quantum computation. Namely, unfortunately, I have nothing that I can draw on here. Or can I? No, I don't think so. So let me say it in words. It is a bit complicated, but let me say it in words. So in this adaptation business, a distinction is made of so the Pauli operators in question, I mean, what used to be the stabilizer operators, the Pauli operators in question here are the byproducts. And they are just updated as you would in the Gottesman-Nil theorem, say under your unitaries. And now a distinction is made when you're propagating a byproduct operator past a non-Clifford gate, like the X or Z. That's the part we have seen. So the rotation angle is flipped, which is compensated by a flip in the measurement angle. But when you propagate this byproduct past the Clifford gate, then it's the other way around. In that case, the Pauli operator is conjugated under the Clifford gate. So it's exactly the other way around. And so the byproduct operators change in this way, and the Clifford gates remain unchanged. And that is why. If there's a non-Clifford gate, it is changed by conjugation. But if the Clifford gate is propagated through, then the gate doesn't change. Only the byproduct operator change in this very predictable Gottesman-Nil type of way. So that is the difference between non-Clifford and Clifford in measurement-based quantum computation and how it relates to the stabilizer formalism and the Gottesman-Nil theorem. Thank you. Yeah? Thank you. Yes? Yes, there is a thing that corresponds to it, that corresponds to match gate, and that is, I mean, the toric code is going to come up here in fault tolerance. It's assuming it works out with my schedule. I don't know where I am in the presentation. Left for the whole thing? Okay, for this. Okay, we can get it started. Anyway, so you could think, okay, let's forget about fault tolerance. Let's use the toric code state or some surface code state as a resource for measurement-based quantum computation. What do you get? And the somewhat disappointing result is that you're getting match gates. So that there is indeed that connection. Yeah, good. Okay, so yeah, thank you. So you were thinking about something, seems to me. No, you. Okay, good. Yeah, okay, good. Yeah, I can point you to one or two references for that. Okay, good. So that was, and also for later, there's a bunch of references here, if you like. So let me, yeah. Okay, so let me tell you a little bit about fault tolerance. And you, Nadim, you just cut me off at the 60-minute mark. Yeah? And where is this? Full screen mode. Okay, here we go. Yeah. Good. Okay, so I just want to tell you a little bit about it. Okay, so this is a quantum architecture talk. Yeah? So there is quantum computing theory, and part of that is the theory of fault tolerance. Over here, quantum computing experiment is also roughly clear what this is supposed to be, but in between we have this layer of architecture. So we want to make quantum error correction suitable to experiment by just realizing that in experimental settings you may not have all the gates available that you want. For example, there might be constraints on who can interact with whom. And it is in this spirit that our error correction work was done. So let me tell you about that. So here's our setting. So we have lattices in 2-dimension or 3-dimension, and we only have nearest neighbor interaction. Yeah, so that's all there is. And now the question is this a huge penalty? If you cannot have qubits interact across long ranges, yeah, does it penalize you a lot, or is it maybe not so bad? Yeah, so that's what this work is about. And I say 2D and 3D because that refers to circuit model 2D, cluster state 3D. There's always this pairing. Yeah? You can use these ideas in both. Yeah? And the threshold is higher, so that's why. Good. Okay, and there's topological stuff in here. So that where we have certain defects in these lattices, 2 types, and they braid in certain ways and fuse and so on and so forth. And in these knot diagrams, we find entangling gates. Okay, so I would really have to race to get there. I need to see if that actually works out. Maybe, well, we'll see. Good, okay. Yeah, so this is maybe to put this value, this threshold value into perspective. Yeah? So we are getting here to threshold values of a good fraction of a percent, maybe 2/3 of a percent. So that was subsequently improved by Austin Fowler and company. I think they pushed it with certain refinements to 1%. So that's roughly where you get 1% of an error threshold. Yeah, it's not the highest threshold that exists. So the highest threshold was established by Manny-Nil, and that's without any geometric constraints. So every qubit can interact with every other qubit, and there's lots of post-selection in there, and yeah, fairly substantial overhead. But I just want to say, yeah, so these are the two numbers. So these are the two best numbers for error thresholds in the absence of constraints, in the presence of constraints. Good. Okay, the two main ideas here, and I'm not sure I'll be able to get to both, but what I want to convey, if I manage somehow, is that the cluster state is a fault-tolerant substrate in 3 dimensions, not in 2, but in 3 dimensions. So it has error correction built in. That's the first point. And the other point is now you can do some drilling of holes into these cluster states. And that gives you additional capability. No? So that gives you now the capability to do fault-tolerant quantum gates in a topological fashion. Okay, good. So let's see. So this is a macroscopic view. This is a 3D cluster. There's now 3 types of regions in this cluster. I will mostly talk about 2 only today. So there is these defects that I already mentioned. This is just missing cluster. Then there is the bulk of the cluster. And then there are these singular qubits, as we called them. So these 3 regions of the cluster are distinguished by the measurement basis. So the bulk, or called vacuum here, is measured in the X basis. So that's dominantly what's happening. Nearly everything is measured in the X basis. So these line-like defects, the holes, they are measured in the eigenbasis of Z. And then you have these singular qubits that are measured in, say, X plus Y. I'm not going to talk about them too much today. So these qubits are for magic state distillation and non-Clifford gates. Good. So that's that is the macroscopic view of the scheme. So now we want to make sense of this. And to make sense of this, we start at the opposite end. We talk about the microscopics. Yeah? So at the microscopic level, what you see here is the elementary cell of the cluster lattice. Yeah? So you have these edges as usual in the cluster state, so they represent conditional phase gates if you like, easing interaction, anyway, just a way to define the states. And so you have qubits sitting at the centers of these faces in the elementary cell and on the edges. You have no qubits in the corners and no qubits in the centers. So that is the lattice we are dealing with. Okay. And just maybe a little bit of a mathematical comment here, but it will come up later. So there is a lattice duality in this setting. So you can observe, so the cell kind of tiled arbitrarily often in all 3 directions gives you the total cluster. And now you can think of translating this lattice cell by half a cell in all of these 3 directions. And what you see, what happens then is that the cluster actually maps to itself. So an edge qubit will become a face qubit will become an edge qubit, but as long as you don't care about that distinction, the cluster is remaining itself. However, this lattice structure evidently is not mapped into itself because, what used to be a corner becomes a center and the other way around. Yeah? And that's why you have these 2 equivalent lattices through which you can describe the 3D cluster. We call these the primal and the dual lattice, and because you have these 2 lattices, many objects here occur as primal and dual. I mean, everything we care about occurs as primal and dual. Good. Okay, error correction. Good, so let's talk about how you would do error correction here. Yeah? So again, we have the cluster state stabilizer generator. An X in the center and Z's around on the nearest neighbors. So you could think, okay, so let's measure that guy, yeah? Okay, unfortunately, this is all done by local measurements, so we have to measure locally. Still not a problem. We measure this guy locally, measure these Z's locally, and then post-process, multiply the measurement outcomes, and we are supposed to get +1. Okay. Yeah? Every measurement outcome would be individually random, but you expect this correlation. Okay, but there is a but. This is not what we are going to do. And that has to do with what I told you earlier, namely that if we are on the bulk, which is mostly everywhere, we don't have the possibility to measure in Z because everything is supposed to be measured in X. Okay, so that means we are looking for elements of the stabilizer that we can measure, and they are those that have only Pauli X's in their support. Yeah? It's only Pauli X's and identities. That's all that we can read out. And so now the question is, are there any of those, or are there hopefully many of those? Yes, and there are many, and here you see one of them. It's a very small thing. Namely, you multiply the stabilizers associated with the individual faces across all the faces in the boundary of one cell. Yeah? And so you see this Z over here drops out because it receives a Z from the stabilizer centered here, and it receives another Z from the stabilizer centered here. Yeah? Both contribute to what's going on here. So we have a Z squared, which we know gives us the identity. So all the Z's cancel. This is exactly the effect we wanted. So this is a stabilizer now that is built from sigma x's only, and now we can measure in this local fashion. Yeah? So we measure these 6 Pauli x's, they give us random values, but if there's no error, they are supposed to give us the product of +1. If there is an error, then we get a -1, and then from that information, we need to figure out what the error was. Okay, so that's the idea. These will be the stabilizer elements that we measure, things that live on the boundary of a cell. Okay, good. Okay, and yeah, as I already said, if the product evaluates to 1, then this indicates an error. So we have 1 bit of syndrome per cell. Okay, and now say if you have an error here in this qubit, it will flash with a syndrome here and there. And so every error leaves a characteristic error and by which we can identify it. Of course, there's misidentifications as usual in quantum error correction. Good. Okay, so that's basically what's going on here. And the error correction is well understood. That follows from this, and it can be mapped to a StatMag model. But really, I'm racing, so just want to tell you that this mapping exists. Yeah, Nishimori physics exists. You can read it in this. Oops, you can read about it in this paper. Yeah, there's a lot of StatMag connections, as very often in quantum error correction. Okay, yeah, so from that mapping to the StatMag model, we know what our error budget is. It is distributed among various gates that are used in the process of making the cluster states and measuring them, and so this 3% error budget is subdivided between these contributing gates. That's why you go from 3% to 3/4. Good, so, few minutes for this part or overall? Okay, what does few mean? Coming to a conclusion. Okay, good. So let me just tell you, had I been able to speak a little faster, we would have, I mean, we are now about to discuss the gates, the topological gates. What can I tell you about it in a couple of seconds? So I want to just say, 3D cluster state is 3D cluster state measured in the X spaces is basically a surface code propagating in time. Yeah? Circuit model variant, measurement-based model variant, but exactly the same situation. Just want to point that out. And now it turns out you can have you can have surface codes with holes in it. It's just internal boundary, and that gives you qubits. Yeah, so encoded Pauli operators shown here, like so, Z and X. And I know I'm out of time, but yeah, here your encoded qubits again, primal and dual. I told you there is this duplication. Yeah, and then had I had the time, you see, I could have shown you a simple CNOT gate, but you see the explanation of it with all that notation put in place is now quite simple. So the propagation game that is always played in the stabilizer formalism now becomes a topological game. Yeah, you pull a string which represents an encoded Pauli operator, you propagate it along, and it needs to remain attached to these defects, and you see the other defect gets in the way. So it can't stay what it was, and so it changes and changes and changes, and it changes into a correlated operator of X and X, which is one of the propagation relations for the CNOT. Too much information in too little time, but I think you get the idea. Yeah? So the remaining propagation relations are just the same, and together they define the CNOT gate. So this is roughly how this topological error correction works. And yeah, so you can ask me more if you're interested. I also can point you to references, but that is basically the end of the second part, and we have a break now.
Thank you very much, Robert, for that very inspiring talk. So the idea for the format now is that we would take a couple of minutes just to discuss with the people immediately around you how you found this talk, and if you have